So B, right, calculate the energy of the 5 lowest energy levels of the electron in a 2D box with Lxy is equal to 1.5 angstroms, right? Identify which combinations of Nx and Ny are degenerate. So one thing that we have to do, right, is we're going to use that equation. And so because both Lx and Ly are going to be equivalent, right? They're both 1.5 angstroms. That makes our equation a lot easier, right? There's no difference between the two of them. If there was a difference, all it would do is just make the equation a little bit more complicated and annoying, but we don't have to worry about that part. So now the things to pull out. So I have the equation there. I just need to put up right the constants that we're looking at, right? So we have h, which is Planck's constant, so that is 6.026 times 10 to the negative 34 joule seconds. And so one suggestion that I'm going to make, and so this is one that I had made last semester as well, is make yourself like a Google Doc or an Excel file or something where you just start putting like all the different constants that we use in this class into there, right? And then also start putting all the equations into there as well, right? Start making your own equation sheet, your own cheat sheet, right? Because again, right, the exam is open note, right? Open, book and everything like that, right? We're not, doing any kind of, checking on whether or not you guys are, going to other sources. But so that'll make your life a lot easier, right? If you have everything formatted and set up in a way that you did, so that way where everything is, instead of us giving you an equation sheet and then you spending a few minutes of your exam time scrambling to figure out like, oh well, where's the equation that relates to this, right? You can have it all in whatever order that works for your brain set up, right? And so in terms of like putting constants in different things, and then that way too, right, you can also have things repeat easily, right? Because it's just simply copy and paste. And so you can be like, okay, right, even though I need Rydberg constant for these different things, instead of having only one area with the Rydberg constant, right, you can be like, okay, right, I'm just going to put it next to this other equation that I know I'm going to use, so that I don't have to like search around for it and be all frantic during exam time. So that's just the tip for this semester, right, with the whole remote thing. Yeah, right, so H is this right here. Next, right, the other constant that we have is the mass of an electron. So the mass in this case is going to be 9.11 times 10 to the negative 31 kilograms, right? L is going to be 1.5 angstroms, right? So L is 1.5 angstroms, and the angstrom is 1 times 10 to the negative 10 meters. So if I take that 1.5 and then multiply that by 1 times 10 to the negative 10, what do I get? 1.5 times 10 to the negative 10 meters, right? 1.5 times 10 to the negative 10 meters, right? So now we're in units that work, right? N is unitless, so that doesn't matter. And as we, had talked about in the past, with a different part of the problem, which I'll get to at a different point, right? All that stuff cancels out and you end up with joules as your final answer. So the way to approach this, right, is that we have the equation right here. So the first thing that we're going to look at is the E, where the Nx is equal to 1 and Ny is equal to 1, right? That's going to be our ground state, right? Because that's the lowest values of N that we can have in these cases. And so, it just becomes a plug and chug scenario, right? So we have H, which is 6.026 times 10 to the negative 34 joule seconds over 8 times 9.11 times 10 to the negative 31 kilograms times L, which is 1.5 times 10 to the negative 10 meters squared times, right? And so Nx, right, is going to be 1 in this case, so we have 1 squared plus Ny is equal to 1. We have 1 squared. We take all of that, we plug it in to our calculators. So we have 6.026 times 10 to the negative 34 divided by 8 times 9.11 times 10 to the negative 31 times 1.5 times 10 to the negative 10, right? And then we multiply all of that by, oh, I forgot the squared. Right, let me just double check, right? 6.06, which is 6 times 10 to the negative 34 divided by 8 times 9.11 times 10 to the negative 31 times 1.5 times 10 to the negative 10 squared. Oh, I forgot to square the h. That's right. So the reason that I'm doing this is because as I'm looking at it, the scale seems kind of off, right? So at first, what I had gotten before I squared the L was 551,000, and I was like, that doesn't seem right considering everything that's involved. 6.626. It is. Yep, that's what happens when you write things sloppily. Thank you. Again, right? So one benefit of me doing these streams is that it shows very common places where you can mess up on an exam and you can get the wrong answer. So writing things out sloppily, right? So you saw that last week when I was confusing myself like crazy. You're seeing that here, where if I write out, if I transfer something very sloppily onto my paper, I then transfer all of that sloppiness all the way through. So make sure, right, you're just writing slowly and you're being diligent and you're double checking everything, right? Because you don't want to lose, when it comes exam time, you don't want to lose points for something that, right? And so I also missed as a, right, that should be squared, right? So you don't want to lose points for something that is completely avoidable, right? Where it's not like a thing where it's like you don't understand. It's a thing where you just simply transferred something incorrectly because you were being sloppy, or you being fast, or you just weren't paying attention. So you always want to take the time, work your way through slowly for all the problems, right? Even if you know how to approach it really fast. Right, it's very easy to like miss out on small things when you're carrying things over and make mistakes, which is what I would have been doing at this point. For this problem. So, right. So at first, and so the reason that was realizing myself that I was getting the wrong values is because the scaling was off from what I would expect, right? Because I got 551,000 the first time around when I didn't have any squaring, and then I got 3 times 10 to the negative 15 when I squared the length but didn't have the thing. But now where I squared Planck's constant as well, right? Now I'm in a region where I'm expecting to be, which is 2.2 times 10 to the negative 18, right? So I know from experience that the energy values for all of these different things in joules are going to be hovering, very closely, in the region of 1 times 10 to the negative 19 joules, right? That's the rough region, right? Because 1 electron volt is 1.6 times 10 to the negative 19 joules, right? That's going to be where I would expect in terms of scaling things to be. If I'm getting extremely, positive number, or not positive, but extremely, above zero numbers like I was doing at first, right? To me, that was triggering a response where I was like, this doesn't seem right. Something is off, right? And that's just something that you need, that you're not going to have at first. And that's why, some of these problems, they may seem kind of as if you're, it's, just repetition over and over again, but it's to get you comfortable with thinking about, okay, well, what's the scale that I should be at for my answers, right? And so in the cases of all these quantum things, right, when we're talking about, the energies of the orbitals, and then also, the wavelengths and everything, the scale, right, should be hovering around 1 times 10 to the negative 19. You can still make small mistakes, right, where, if you're not paying attention and, instead of meters, right, you would use centimeters, right, you'd still be hovering roughly within that range. And so you may not catch that one initially. But if it's like some major thing where you're forgetting to square something, right, that's where it's really going to come out in those cases. So those are just some things to keep in the back of your minds also, right, when working through these problems, is thinking about, well, does this scale make sense? Instead of just taking what you have in your calculator as canon. But yeah, right. So what I got was for this whole part right here. Oh no, it happened. That's why I shouldn't be messing around with the thing. Okay, right. So I got for this whole part right here. The value is 2.214, right? We'll just go a little bit further with the sig figs times 10 to the negative 18 joules, right? So that's for that part right there. And the thing is, if nx and ny are always the same, like 1 and 1. Anim, is there a second part to that question? Yeah, right. So here, let me finish working my way through this right here, right? So that first part right there is always going to be a constant, right? Because it's all constants for this specific problem. The only thing that can change hypothetically between different types of problems, right, would be the mass or the length or stuff like that, right? But if you're working through and you're just simply calculating what all the different energy levels are, you can make your life a lot easier if you just calculate what that first thing is, and the only thing that you have to really change is just simply the nx and the ny values in those cases. So we know then that right that first part is equal to 2.214 times 10 to the negative 18 joules, and so we can take that and we can multiply that by 1 squared plus 1 squared, right, which is just 2. And so what we get then is the value is 4.429 times 10 to the negative 18 joules. And I apologize, I have to use my finger right now because for some reason, Surface laptops, am I right? Why is my value slightly different? Oh, because I forgot to change on my calculator. Okay. Here, let me see. Does this work again? Yeah, okay, awesome. Here, wait a second. So this part right here was wrong. Because I was still like had my calculator the 6.026 or 6.026, right, instead of 6.626, right? So this should be all right, this should be 2.677 times 10 to the negative 18 joules. And so if we multiply that by 1 squared plus 1 squared, what we get is 5.355 times 10 to the negative 18 joules, right? So that's the energy of the E11. Right, that's the first level. So if we then go to the next one, right, what we have is right the E21, right? So now we're saying that the nx value is equal to 2, the ny value is still equal to 1, and now we plug all of that in. So we just simply take, our value that we have that we already calculated for that first constant, right? We don't have to go through the whole process of plugging that all in again because, we don't want to make that mistake, right? We can just simply do that. So I can just simply use that 2.677 times 10 to the negative 18 joules, and I can multiply that by 2 squared plus 1 squared in this case, right? So if we do that, so 2.677 times 10 to the negative 18 times 2 squared plus 1 squared comes out to being 1.339 times 10 to the negative 17 joules in this case, right? So that's what I got. And yep, that matches, essentially what I have in the key, right? So then the next thing is, right, the next combination we can have, right, is that we can have nx is equal to 1 and then have ny equal to 2 in these cases, right? That's technically a different state, right? Because now the wave function for the x direction, right, is going to be just simply, n equals 1, and then now the y direction is n equals 2, and so that's going to give you a different looking, map, right? That topographical map if we were going to do it in the thing. But if we do the math part of it, right, we can just simply, again, use that constant we have. Now it's 1 squared plus 2 squared, right? If you plug that in, what you'll get is the exact same answer that we got for the 2-1 combination, right, which is the 39 times 10 to the negative 17 joules, right? So that, right, so those two values are going to be the same. Even though they're technically two different wave functions, right, because one has the x direction being, n equals 2 and ny is equal to 1, whereas the other one has the nx is equal to 1 and the ny equal to 2. They're different wave functions, but they have the exact same energy, right? So both of those are going to be degenerate, right? Because what the meaning of degeneracy, right, means that they have the exact same energy, right? They're two different things, but they have the exact same energy, which makes sense, right? Because all we're doing is just simply, in a way, right, just simply flipping, that map of what that total wave function looks like, essentially along an axis, in those cases, right? There's no difference between the two of them, right? They're just like mirror images of each other. Right, and then you can just keep working your way through. I'm not going to do the rest of them, right? Because all it is simply plug and chug, right? You just simply then do, when nx is equal to 2 and ny is equal to 2, you plug that in, you get a value. You can go then to nx is equal to 3, right? And the one thing to think about, is it's very easy to skip over combinations of numbers, right? And that's kind of like a tricky thing for this right here, right? Because I was asking for the 6 lowest energy combinations, and so if you didn't think that the 3-1 combination, existed or was going to be, lower in energy than the 2-3 combination, right? Which if you're going, 1-1, 2-1, 2-2, right? The next thing in your mind is then 3-2, right? But you're forgetting the combination of 3-1, right? That's still a combination that can happen in those cases, right? So you always have to be careful in those cases of jumping to which one you think is next, right? Because the 3-1 combination gives you, for this part of the bracket, right, the 3-1 combination gives you 10, whereas the 3-2 combination, right, that's going to be, 3 squared is 9, 2 squared is 4, gives you 13, right? That's a pretty big difference in number between the two of them. But right, that's how you approach B.